So I think we can start. I'm not going to speak a long time. I think about under 1 hour, but let's see. I have not yet published this course material in itslearning environment. I'm going to publish it this week. So the first working week is next week. And we can first check the specification for this course. So on the right side is English version of this course material specs. There is these common things first. What is the aim for this course? To students understand the meaning of strength analysis with respect to safety and structures and in economical use of material. Also can design relatively simple structures where the force quantities can be evaluated by means of static equilibrium. Stresses and deformations in axially loaded members who shared stresses in beams and screws, the principle of torsional stress, force and moment diagrams in beam bending, stress section modulus and bending stress in beam bending. The exact timetable can be found, of course, in itslearning environment. And as in autumn course, the mechanical engineering course, this course is also so-called flipped learning. So I'm going to stream all these lectures and also record them to the same Teams as the earlier course. And I put those links to this material also, so you can find them. And also this recording now, it goes to your Teams environment. You are used with this flipped learning system, so I don't think we have to. This is also important. You can use artificial intelligence when you are solving your exercises, but put a mark IA when you are solving those. So it's okay to use, but you have to inform that you have used IA help. This Copilot is quite good IA system, and you can use it freely. And because it's our uni have paid for this Copilot system, it doesn't go to the global IA systems, but you are calculating or making text or something like that. It's closed environment in our uni. Same system as in autumn course. First, I give you an brief lecture what the week's theme is, and then the rest of the time we calculate these exercises. Perhaps a little more than 30 minutes because I'm trying to record for the future use also this part of theory and then those tips for exercises. And as in autumn, you can also participate remotely. Yeah. Here are some examples. There are much online material in internet to find in this subject, and I put those links when I publish the It's Learning environment, and you can find those materials in English easily using those links. No. And the evaluation is similar as in autumn course. In autumn course, there was, if I remember correctly, 27 exercises. Now I think there is something like 14 exercises, and you can pass the course by uploading your exercises, and if they are correctly solved, you get the points. And I think it was so that you can left only one. I'm not sure. I don't remember how many exercises there are, but it's not so many than it was in mechanical engineering course. But same system as in autumn. You can pass the course with exercises that you have uploaded. And if you like to have better grade than one, then you have to come to the exam and try to raise your grade. So this is the specs for this course. And because I have not published yet the It's Learning environment, I'm going to show you an PowerPoint so that is from whole course material. So we're going to check the whole course material. Like a speed lane show. Okay. And this material is from this International Welding Engineer course. But I have selected the parts that is for you suitable. So here are these subjects. Okay, this is the as you can see those pictures are similar that was in Autumn's course. But the first subject, normal force in a beam, and in a beam, if there is a joint in both ends or are hinged at both ends, as we talked in autumn, it can only transmit force along its own axis. And this was this constructions that difference from this. You can call also this a truss construction. But if there is a force between those joints, then the force can be at any direction, not just along the axis. And this is as those pictures that we discussed already in autumn. What happens if there is a force at both ends? What happens in the middle? And the answer is that in the middle is exactly the same force, because if we got section from this beam, this section has to also stay still. So if there is 2 kilonewtons, there have to be also 2 kilonewtons. And those Mark rules that we discussed at autumn, of course, they are just exactly the same. But this is new. The force per area divided by area is stress, and we use sigma sign. Oh, it doesn't show my. Let's so this is first rule, force divided by area, and this is stress. Yeah, and we use this when it's normal stress, we use this sign sigma, and the unit of sigma nver millimeter over 2, or it is as great as megapascal. So it's quite convenient unit to use, because from this material science that you have studied, those strength units were also megapascals. So that's why we must use the force unit Newton and the area unit cubic millimeter power 2. Next one that you can find from here is shear stress. And shear stress is a little bit complex because the material doesn't have as much strength when it's shear stress than it has in normal stress. It only about 60% what material can bear shear stress combined with normal stress. And if we are making axles, there is all of course torque in the axle, so this shear stress can happen if we cut a sheet or we put moment torque to the axle. Both way happens this shear phenomenon. So it writes in here, materials are less resistant to shear than tensile, compression or bending. And it's about 60% only. So here's the equation. If there is no information about how much shear stress the material can take, this is a convenient equation, and we use different sign for the shear stress. This is tau from Greek alphabet, and this is the sigma. So this is sigma, and I put this. This is Finnish word sallittu. It means that what's the maximum value for that's because I noticed that in this formulas book also was used Finnish letters, so that's why I did put also in Finnish letters in here. Okay, and in this picture, I have tried to explain why material is more resistant for tensile than shear. And the explanation is that when material is under tensile force, these atoms that are nearby are holding the material together. And the atomic force is bigger when the atoms are near each other. And when you have a shear force, the atom forces have to be like that to put so that these atom dislocations don't leave moving, and this is longer distance to hold atoms together, so that's why the force is not so big when there is tensile shear stress. The difference is those atom forces. So the distance is the main thing. But the shorter distance, the stronger material. And here the distance is longer, so these atom forces are not so strong. This is something that in the beginning of the course also. Every time that we put tensile, the deformation happens, and we can calculate these deformations if it compression, so it's the piece comes shorter, and if it tensile, the piece comes longer. And these equations, linear strain is change in length per original length. And here's a normal tension equation. Stress, normal stress increase can be calculated for the area. And of course, those chain rules are also in the picture. And this is the shear strain. So here is an example when there is a sheet cutting machine, what happens in the plate. And of course, this kind of situation, the deformation happens in angle. This is important picture. I have translated those, but I tell you what they are. So this area is the strength of material area, and we can't over the yield strength, because if we do, the plastic deformation happens. And if we are trying to build different kind of structures, we don't want the deformation. And over this yield strength is the production technology area. And if we want to bend the structure, some kind of deformation must be plastic. So this strength is elastic area, and this production technology is plastic area. And this maximum strain line, there is over the maximum strain line, there is this cutting technology. And here is deforming technology under. And this is Hawke's law, which means that if we know this linear strain epsilon and we know the materials Young's modulus is E, we can calculate the normal stretch that happens in the particle. And when we combined these three rules, we get the equation from which we can calculate the deformation stress-strain relationship. And you can see the formulas, how it's done. Here is the Hooke's law. Here is the force per area. Here's the delta L per L. And we put this one in the place of sigma and this one in the place of epsilon. Then we can calculate the delta L. So it's the lengthen of this value is the lengthen deformation of the piece when we put some kind of force in the piece. So this is very useful equation or formula to use when calculating the deformations. I think this was your same. There is two kind of methods when we are designing structures. We can use this service limit state, or we can use this ultimate limit state axis. And it means that when we use this ultimate limit state, we are just the values are limited only by the yield strength value. Of course, there is safety factor. We can't go to near this yield strength because of if there is overload stress. So then the plastic deformation can happen. And in this axis, the forces are limited by deformation. And actually, most design is done by this service limit state. So when we are designing a structure, we decide that how much, for example, this table can bend when we put 100 kilos on it. And of course, table can take much more force if we are using this ultimate limit measure. And when we use this service limit states, for example, if we are designing a floor, we know that floor can bend without breaking many tens of centimeters, but it's useless if it bends so much. So that's why we use the limit, how many millimeters per meter the floor can bend, so it is usable for normal use. We can also draw same kind of picture for the shear stress. So this is a shear stress limit drawing that you can see. And the difference from this tensile stress picture is that this shear module, we use alphabet G, when in this tensile we used alphabet E, so Young modulus. And there's a mathematical connection between this E and G. And at the same reason that material is less strength in shear load and in tensile load. Also, this G value is quite a bit. This is steel's E value is 200 about gigapascals, and this is about 70 gigapascal, this G value. So also deformation in shear stress is greater than tensile stress. And this picture is about the deformation picture. If we pull a piece longer, there is not going to be any atoms more from the pulling. So there is two possibilities. Even it is possible that atoms, just the distance between atoms, get greater, or it is possible that the deformation in other dimensions can be the measurements in other dimensions shorter. And if you think about rubber, if you pull rubber string, you can see how it how the deformation affects the other dimensions. So actually the volume of this rubber string stays same even if we strengthen if we pull the rubber string. But actually most of materials, the volume of the material diminishes when we are pulling the material, and also in other way if we are compressing. So some of these volume differences is affected by the atoms moving, and some of it, the volume differences comes from this, that atoms are much, the distance between atoms gets greater. Here it is E values. So aluminium 70 gigapascals, steel 206 gigapascal, concrete, wood, plastic, and the greater the Young's modulus is, the stiffer the material is. So it's good that in steel the Young modulus value is very big. And safety factor is the next shown here. Safety factor when we are designing structures, we can't go too near the yield value. So that's the safety factor. And here are some examples how big is the safety factor in different situations. I many times use 1.5 safety factor. This was same. And here the equations for safety factor. Critical stress per permissible stress. Here are collection of different kind of stresses: tension, compression, bending, buckling, torsion, shear. We are going to watch all of these during the course. Sorry, buckling is not included. Tension, compression, bending, torsion, shear. And in different kind of structures, these different kind of stresses can happen simultaneously. For example, in this picture, if there is force, it bends here, it bends here, it's same times there is torsion and so on. So different kind of stresses combined same time. This is the most important part in this course, the bending, what happens in the bending, because these stresses are the biggest stresses that happened in structures. And you can find these pictures from this formulas book. So it is important you have this formulas book so that you can find. We need these formulas. We have to calculate the maximum stress, so we can directly find the formula from which we calculate this moment value. So that's why we studied in this technical mechanics course. We studied these stress diagrams or load diagrams. Process section values is something that we need also in bending, and also there are different kind of methods that we can use when we are calculating those cross-section values. The bigger cross-section value is, the less the beam is bending. And also in torsion we calculate, but the equation is a little bit different in torsion. This is normal force calculation. It's something that we start from. Here is some example how to calculate stresses, and also from this chain, what happens in chain. Here are these bending examples, calculation examples, and this is the most important part in this course, how to calculate these stresses in bending. Shear stress calculation. And torsion also is shear stress calculation. Here is also an example how to calculate. This is von Mises hypothesis. You can calculate when there is simultaneously bending and shear in two-dimensional shear, or here is just normal force and shear force stress. How to combine those. And also we can use these equations that when we want to know the power in axle, we take this torque Q and angular velocity, and we get the power value in axis. Here an example of calculation in torque Q. And here, of course, deformation happens also into torsion. And here are the equations that we can use when we calculate the angle of the twist. If you use radius value, we use these two equations. If we want to have degree value, we use these equations. And then there is an example of bending and what happens in piece when we are bending. And also is an example of calculating the power and also this torque Q that happens when we use some kind of power. There are some examples of failure. Actually, this is out of our area. This fatigue phenomenon we are not going to even though it's most common cause of mashing parts to break, it's not included in that our course. So I think we can stop to here. And as I said earlier, I'm going to publish this e-learning material in this week, and next week comes the first exercises from that. So we stop here. Stop here.